Okay, so we'll pick up where we left off last time, which if you recall, we were working on talking about the types of flip-flops, right? So we went through JK, T, D flip-flops, and we started building these into asynchronous counters that behave kind of like the full adders, right? That have this kind of cascade of delays, and they're slow, but kind of logic minimum for a counter. Then we moved on to do the synchronous counters, which have a little bit more logic, so they take a little bit more area, but they are faster. So now what I want to do is kind of, did I talk about how to reset counters because when you count, right, if you have we'll do the simplest case, well, a simple case, a 2-bit counter. That if it counts up to 1, 1, right, the next number that you would count up to would be 1, 0, 0. But we don't have this bit, right? So that bit just goes away and we're back to 0, 0. We wrap around. So it's easy to count 2 to the n times. So if I went and I had a counter that has, right, a clock is what that symbol means. It has an enable because I either want to be able to count or not count. And then it has 4 bits. How do I count to a number that isn't 2 to the 4 using that counter? And really it's 2 to the 4 minus 1, right? Because it starts at 0. How do I count to a non 2 to the 4 number using this if I also add the resets? Any ideas? Idea?
You take either that number or the number right after it, figure out some logic to only accept that and put that back to reset.
Yeah. And I will illustrate that for you guys to make sure that this makes sense. Sorry. So this is row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There. So what he's saying is we want to build some logic that more or less detects when we get to the number. Let's say I want to reset at 9. I want to count at 9 and then go back around. I don't want to reset at 15. He says, let's make some extra logic that says, when is this? So what does that logic look like? When can I say that this is detected?
You use an AND gate to determine when it hits that point, you would reset the count back to 0.
Yes, exactly. I would just use an AND gate, right? It's just take the min term of this row and would say, well, it's bit 4 and bit 0. Well, sorry, bit 3 really, because we're 0 indexed. And then we take not bit 1 or bit 2. I feed that back around in the reset.
So honestly, you wouldn't even need to do the 4-way AND gate for this one because that's the second term where bit 3 is there, and you don't care if it triggers on ones after that because it should trigger before those.
Exactly. So what he's saying is, and this is, I was actually going to bring this up, but what he was saying is these two are irrelevant because The first time that I have B, I'll write these out. B 0, haha, that's what I did wrong. B1, 2, and 3. The first time that I have bit 3 is true and bit 0 is true is when I reset. So anything after that is don't care. It doesn't matter because I should never get there, right? So these two middle ones can just go away. Now keep in mind that for this to work, this reset needs to be a synchronous reset so that we, well, should be a synchronous reset because otherwise the moment we hit 9, like the very second we hit 9, it's going to reset and we're never going to see 9, right? It's going to be like this infinitesimally small time, whatever the gate delay of this AND gate is. So if we want it to stay there for whatever duration, a clock duration, then we need a synchronous reset, which I'll do the timing diagram, I think, in just a minute. All right, so now we've counted to 9. We can do this same operation, right? We can prove that this logic works, not just through the recognition that this is true. We have tools that allow us to do this kind of logic simplification. What tool would we like to use, perhaps?
Like what tool?
To simplify the logic, right? So that you don't have to just recognize this pattern works. What would we go through as a logic simplification tool? What do we have? What tool do we have to simplify logic? A K-map, guys, right? Pulling back to the land of the K-map. So let's draw a K-map for reset. When do I want to reset? Well, we can just start counting up for the times that I don't want to, right? So um, 7. Four variables is a 4-bit K-map. So then I just say, I know I don't want to reset until 9, right? Definitely reset at 9. That's what that says. Now, everything after that should never happen, right? So the two ways we could do it, the less correct way is write 1s at all of those, which would say, like, if you ever ended up in this state, reset because something weird happened. But really, we would like to say that, well, we should never end up here. So we can just fill in the rest of that K-map with don't cares. I don't care because it should never happen, right? That's one of our conditions for don't care. So what do? Well, this K-map, I only have 1, 1. Yeah, exactly. So what do I want to circle?
Just the one, or you could circle also the don't care, so you can do like 4.
Yeah, exactly. I can do the square of don't cares. So if I did just the 1, that's not the simplest term. That would give me the 4-input AND gate. By having these don't cares around it, I get a 2-input AND gate. That if you finish off the K-map, you get B0 and B3, right? So as long as we set our K-maps up correctly, that is how we're going to figure out the logic for when to reset. Now, let's move on and make this a little bit more complicated, I guess you'd suppose, and say that, well, I want to have a 2 digit BCD counter, binary coded decimal. Does anyone remember what binary coded decimal is? Okay, so BCD is probably going to end up on the exam, just so everyone knows. BCD is where we take 4 bits and assign it to a decimal number. That's why I stopped at 9, right? This is your alarm clock. We tie it into the 7-segment display, right? And then each of these logics correspond to lighting up 1 decimal digit. And so after 9, we don't care because I can't represent 10 on a 7-segment display. That's what BCD is. It's just coding decimal in 4 bits of binary and saying everything else is don't care. Except for maybe like we do E for error, right? That was one of our examples. Okay, so now we have 1 BCD counter, right? It would go up, you go 0 to 9 and then reset back around. You've seen this, right? They have one of these on the FPGAs that we started touching in lab 7, where it just starts as a counter that goes from 0 to 9 and resets, right? But what if I wanted to count up from 0 to 19? I need another digit, right? So I'm going to jump over here to this side. And it too is going to have an enable signal, a reset, a clock, and 4 bits. And it's the same thing, right, where it wants to reset at 9. Well, let's say we want it synchronous. So the clocks are the same. How do I make this count up in the correct way, right? So this one should only count once for every 10 of these. How do I do it? So this enable, let's say, is just 1. It is always enabled.
Would you feed the reset into the enable the next one?
Yes, exactly. So what this says is when this one ticks back over to 0, that means here is a 1. This one says, oh, look, I'm supposed to count once, right? Because the clock edge will hit, the enable goes on, it counts, but as soon as it's done with that count, that means this one has moved on to the next number. The output of the AND gate is no longer true. We're no longer enabled. Everyone see that? And we can do things, we can add like an extra complication, like instead of reset, we could call it load, and we could give it like a 4-bit load input. And instead of resetting from 9 back to 0, we could go from 9 to like 2, right? Because last time we talked about that parallel load circuit, I believe. Did we get there? Anyone? Or did I not get there yet? If I didn't get there, that's fine. I'll move on to that and talk about how would I do a parallel load to get a non-zero reset. Okay, so I guess we haven't done that yet, so I'll go ahead and that's what we'll do that. So this is a 2-bit BCD counter. And so I guess that's a good segue. Let's say I want load. And I'm going to call this load val. And instead of reset, I'm going to call it load. So that when this gets asserted, I pull in whatever 4-bit value is presented to the load val input. So for example, this could be that, right? 0, 0, 1, 0. I don't want to go back to 0 for whatever reason. This happens, but how would we build that circuit? Okay. So the first thing that we do is we remember that we're building these counters out of flip-flops, right? And what's nice to use is when we're building these D flip-flops, they have really the easiest use case, right? Where we just, whatever happens at D gets put on the Q at the rising edge of the clock. And then we have, all right, and we're gonna build this one synchronous. Right, synchronous clock. And a simple test question, maybe I draw a circuit like this and be like, here's a counter, is this synchronous or asynchronous counting? Okay, now, if I always want to, I'm gonna do this a different way, because the principle ends up the same, because how you wire it. But let's build this, because I want to also review, we talked about shift registers last time, right?
Yeah.
So let's build this, instead of as a counter, let's build a parallel load shift register. And it turned out you can use shift registers as counters as well. But let's go ahead and use this as an opportunity to review shift registers. How do we parallel load a shift register? Did we talk about this one? All right, well, we'll do this just in case. So essentially, this is your input, right? Which we're always going to take an input on every clock edge unless we have an enable. I'm not going to build an enable. That's fine. We then need some simple logic that says if we want to shift, then we shift. Otherwise, we load. Well, the default situation for like a DQ flip-flop shift register is this, right? And so every time a clock happens, it's going to shift. But we need to say, hey, maybe not every time. So we're going to break that connection and insert some logic between the two of them. And then we can do something like, well, I want to select whether I am shifting or loading. Okay, well, when we say select, we really mean like a mux, right? Okay, so here, if I say 0, so not shift, if I have a 0 here, I shift, right? It functions as usual because I've selected this input to put into DQ. So in the case where S, I'm going to call this S, I'm going to call it SH for shift. That says if 0, do what you usually do. Otherwise, let's put in a new value. Call that P0, right? Where if I say load, instead of getting the input into the next flip-flop, I get whatever P0 is. And it could be a 1 or a 0, right? And it's just based on this shift or load. That's all. And if I insert that same logic, right? I've now got a 2-bit load or shift register. And then we could rethink this, right? And start thinking about, well, what would we do with a counter? Right? So counters are going to say something like, let me pull, make sure I do one of these counters right. Then we can start thinking about it. Are we okay if I erase this? Okay. So one form of, I want to figure out if I want to do this as an up or down counter. Let's do that. Let's use this same principle to build an up or down counter, right? So we talked about up counters and we talked about down counters. Let's build one that is either. Okay, so we're going to use T flip-flops because in my opinion, those are the easiest ones to build counters out of. And I'm going to be lazy and I'm going to go ahead and try and make this an asynchronous counter, right? So I don't have to deal with that extra logic and I can do the simplest use case. So the first counter is just the enable, right? If we want to count, we assert enable. And then for the up counter case, we would take Q bar and we would just feed Q bar into the clock, right? Do you remember that? Yes, okay. Well, for the down counter, the only difference was we fed Q into clock. Right? And where this value here is Q naught, and it's the same thing for actually, I'm going to redraw this. In both the case, so I'm going to draw this kind of weird. So the first one I'm going to leave as the down counter, and the next one I'm going to leave as the up counter. And in both cases, the Q is a bit of the counter that we're interested in. So Q0, this is the 0th bit, Q1, Q2, right? Okay, I've drawn them two different ways, but I want to be able to build an up or down counter. Now, using that idea that I just showed previously in the load, can we do something similar here to make an up or down counter? Yeah.
Yeah, you can use that to build an up or down counter.
Okay, so what would I do? I want to build something that could be either one of these cases, right? Yeah.
Would you do like a select thing to choose whether you're counting up or down, and then do branch off separately from there?
Yes. What device would I do with that? Use that. A mux. Now, what's interesting is kind of the question really is which Q or Q bar are we using, right? That's the question. So we'll keep the bit selects because those stay the same in both cases, right? And now it's just a matter of selecting where the clock comes from, right? Well, we established, actually, I'm going to ask, who hasn't really talked here? Jason, what is the case for the 0? If I put 0 into this mux, is it up or down?
I think it's down. I'm not sure.
What output is connected to the next flip-flop's clock if I put 0 into the mux?
I think both 0 and the 1. For 2 to be 0, not Q would be 1, right?
Well, we don't know Q. So I'm not asking for the actual values. I'm asking for the signal name. Really. What signal? So if this is, I'm going to call it, I'm going to use U. So U is a common designator that we use for components on circuits. So get used to kind of saying U's. I don't really know why, but it's always been. So let's call the first one U0 and the second one U1 and the third one U2. Okay. Now, which signal does U1 see at its clock if I use 0 into the mux?
I guess it's not Q or Q bar.
It's actually the other one. So in the mux, it always starts, right? So if I have a mux and I have input, I'm going to call this I1 and I2, and my select is 0, I take I1. It counts top to bottom. So what that means is if I put 0 here, I take Q and route it to the next clock. Is that an up or a down counter?
Down, right?
Down counter, yeah. So what that means is we say not down, right? Because 0 means down or up. Ah, we did. We built an up or down counter using T flip-flops.
And so you just add a mux on the, in between U1 and U2.
Yeah, exactly. We just repeat this circuit over and over again
Okay,
and you would just tie both of them to the same up-down signal, right? Because it wouldn't make sense to have like half counting up, half counting down, unless you wanted like a sequence generator, right? That would generate a reliable sequence, but it would be it wouldn't be a counter. Okay, so I recall we started talking about the shift registers last time, right? And I'm trying to recall how far I got. Did I do this circuit?
I was not here on Tuesday.
You're not here.
So,
Did I do this circuit?
oh, yeah.
Yeah.
I recognize that.
Okay, good. Yeah. So this circuit is the same circuit that's identical. I'll just show this around so that you guys remember, is identical to the mux counting circuit. Because if you notice those AND gates and that OR gate, I'm gonna look. I'll come back to you so you can see too. The AND and OR gate kind of cascade is a mux. It is a mux. So what I drew up today was identical to that. It was just instead of drawing that, I drew a mux, right? Where this works as long as one of the inputs is that. Right? Does everyone see that? So where this would be, what did I call it back then? This was the shift value and this was the parallel load value. That's all. It's a mux. It's the same thing. Okay. So now I get to start introducing some new topics that are kind of fun. that are going to be helpful in designing, and it's going to be helpful in the homework that I've assigned too. The idea, they're called, sorry, let me gather my thoughts right now. I went a little crazy. Generic and generate. Okay, generic statements and generate statements. That's what we're going to start delving into here. So generics are like constants, but they're used at the very beginning of a module of VHDL, so it can change every time you create an instance. Okay, I'm going to say that again. It's like a constant, but it's used at the beginning of a VHDL module and can change for each instance of that module. Why would we want to do this? Well, we could build a shift register, and we will in class, that is n bits. So I would write code one time, and then when I declare that component, it's an n bit component. But then when I create the instance, it could be, I could make one 8-bit, one 4-bit, one 3-bit, however many I want, without writing new VHDL code. The same thing applies for adders. I could build one n-bit adder, and then I can write code one time that then will, on the instantiation, I can choose how many bits of an adder it is. Okay, this is a little bit confusing sounding right now, but fortunately, generics are really easy to use. So I'm going to pull up my code here to make sure I don't get typos. I'm going to start off writing like as good a code as I can, and it'll slowly degrade into pseudocode. So the first thing that I need to do is I'm going to establish that I have a register that I've written, right? So part of your homework that I've assigned, I've told you to go write VHDL code for various types of flip-flops. I'm going to give you the answer to one of them right here, pretty much. I lied. This is pretty pseudocode. Okay, here we go. I've written a D flip-flop with, actually I need to add one more element to ask this question. All right, I've written a D flip-flop. Is this a synchronous or asynchronous reset? Yeah, because it's in the process list, so it can reset whenever, right? All right.
Which is it?
Asynchronous. And that's because it doesn't have to be synchronized to the clock to happen. Are you guys doing okay on this edge readability? Or are you going crazy? All right. Now that I have this register, I'm going to go start and I'm going to build an n-bit shift register. Okay, so this is what I would like to do. I want to say my N shift register is going to be, if you recall, it's going to be serial in, SI, parallel out, right? Because this out is N bits. Well, 0 to N minus 1 N bits. So it's serial in, parallel out, SIPO. But I need to be able to say what this N is, because otherwise it doesn't make sense, right? I couldn't just write that because that's like a constant that hasn't been declared. Well, to do this, and what you would do is between the entity and the port, I'm not going to erase all this because it'll take a long time. So here, I would add a new type of port. Now, to do that, I just write generic. And I say something like N is an integer that is equal to 16. So this line goes after the entity declaration, but before the port. So it just slots in there. And what this says is, hey, there's this new type of port, but instead of being a regular port, it's a generic. It's a variable. I really shouldn't say variable. It's a constant that you get to declare upon initialization, instantiation. And it defaults to 16 as a default value of 16. It can be changed, but if I don't provide it, which I'll show you in the instantiation soon, then it will just say, oh, it must be a 16-bit shift register. Okay, so now I have N available, which means I can actually do this. I can say N minus 1, ta-da, I did it, right? And now I have a variable with port. That's pretty useful. Well, let's keep going on. So I have the architecture, and I'm going to declare that component reg. And I'm not going to fill out the whole component declaration, right? But the way you make that component declaration is you just copy and paste this entity registration, replace entity with component, right? So this is why I wrote this register, is I want you to know what's happening here when I say component register exists. Make sense? Then I begin the architecture. So architecture, declare the component, begin. Now, the one thing I do need to do before that, and you'll see why I don't want to come back and erase this later, is I'm going to have a signal that is going to be an internal signal. So I'm going to call it just int s, internal signal. And it's going to be a standard logic vector that is n minus 1 down to 0. Again, I'm using that n. I'm literally going to write n in my code. Okay, then I can begin. And here's something that's interesting. Now I'm going to build up the generate function. So that's what I said we're going to talk about, right? Generic and generate. These two really go hand in hand very well. But what happens is I'm going to create a number of registers, reg, equal to the number of bits my shift register wants to be. So I need a way of dynamically instantiating components, right? That's what that means. It's because I don't want to write like a bunch of code when it could be simple. And it's going to be fairly short. But it turns out, and it'll make more sense when I've done it, the first shift register is different than everything that comes after. So let's make reg 0 first. I'm going to call it shift 0 is its name. Its component type is register with a port map as follows. Well, the component is D, clock, reset, and Q. My input here, D is just going to be input, clock, reset, and Q, well, I'm going to use this internal signal, right? We've done this a bunch, and I hope this makes sense to everyone at this point. Because if my output is not going to a port, it's going to another component, I use internal signals, int s. So it's going to use int s at 0. Okay, so I am once again going to take a moment to point out I have used an ordered instantiation, right? I haven't done the explicit port declarations. Does anyone not know what I mean when I say that?
So you use it, not an instantiation, you use what?
So I used a ordered instantiation rather than explicit port declarations. Does everyone know what that means by this point? If anyone doesn't, it's really important that you raise your hand and ask.
Sorry, you say that one more time?
Yes, I use an ordered instantiation instead of explicit port declarations. Right, because normally what I would do, what I would expect you guys to do is this. This works. I don't recommend it because it's less clear what's happening and it's easy to mess up because this has to be in the same order as these ports. And if you were to go back and edit the order of this ports, you would ruin your declaration and it wouldn't be obvious. Sorry, it would ruin your instantiation and it wouldn't be obvious. But I'm going to do it because it's going to save me a whole bunch of writing. Okay, so I've made the first one. Now, after that, what you have hopefully noticed is that I keep building like the first and second register. And after that, I just say, and then you keep doing the same thing, right? And then keep going, right? So that's what I'm going to do. And I'm going to build the first and then just say, and then keep going. Why does that work? Well, or sorry, how does that work? Well, this is where generate comes in. It's like a for loop. Just keep going until you've reached however far you've wanted. But instead of a for loop, we use a generate loop. Now, there's this weird thing in VHDL, well, it may be weird depending which programming you're coming from, that we actually get to name our loops. And that's helpful in debug. So the name of the loop is gen shift, generate shift. And I'm just going to write this. Okay, so this name is generate shift. And now I'm going to use a for loop, which we've introduced, right? We've seen it in labs and we've seen it in one homework problem, I think. This says for II. Now, I use II. I use double variable letters for my loop variables. This is called your loop variable. I don't use, so if I had an embedded loop, I'd say for II, for JJ. And I don't really know why, but historically speaking, we always start at I as our loop variable. I don't know why, it's just what people do. As electrical engineers, we hate this. And the reason is, if you've taken any more electrical engineering classes, you'll note that we use both I and J as what?
Complex number.
Yes, exactly. They indicate that it's a complex number. So in programming languages, like MATLAB is one that you may encounter someday. We've kind of phased that out of our program, but you still may run into it. You can write I or J as an imaginary number. Once you've done this, though, it stops functioning as an imaginary number and starts functioning as a loop variable. So anyway, the other reason is if I see an error that has like error I instantly go, oh, that's a loop variable problem. Right? Because it'll say something like, II is out of bounds. I'm like, oh, my loop is too big for whatever vector I declared, right? So anyways, that's just good coding practice. Now, the range, this is called the range, is 1 to n minus 1. Now, VHDL usually would index at 0, but I've already taken care of 0 because it was special, right? So I'm purposely starting here at 1 to n minus 1, which is the n. Again, this n defaults to 16, but gets to be changed. And I'll write the instantiations in just a bit. All right, now let's go ahead and write the loop. There's this thing, I don't really, actually, let me write the code and then I'll talk about it. Okay. And generate. Okay, so here's what happens is shift X, this X, depending on the way that your Vivado environment is set up, when it creates it, the generated name, right? When you click on the hierarchy in sources, it's going to say shift 0, shift 1, shift 2, shift 3. Except for it should start at shift 1, right? It should replace this X. Depending on your settings, sometimes it would come out as shift X1. I don't really know why. I don't actually even know where that setting is, but I've seen it come out both ways. So anyways, it will auto-generate for you, not anytime you instantiate this component, shift X with a unique name that is based on the loop variable. Okay, then I say it has the component type is reg. Its port map is the same type of port map where the first one is the input, right? And its input, notice I said II minus 1. Well, the first loop, II is 1, so II minus 1 is 0. So its input is int s at 0, which is the output of the previous flip-flop. Make sense for everyone? Okay, then its output is int s at 1. Then the next time the loop happens, II is 2, so it takes int s at 2 minus 1 is 1, which was the previous output, and its output is 2, right? And it just marches through building flip-flop by flip-flop a shift register of n bits. And then I just say Q gets assigned, Q being the output to this int s, which is the vector containing all of the shift registered outputs. If I wanted this to be serial in, serial out, I would instead I would write Q as standard logic, and then just say Q is int s at n minus 1. Right? Okay, that same idea works really well for n-bit adders. You would do the same kind of thing, the same kind of generate statement. Your homework is going to ask you to do something very similar to this. Let's go ahead and make the instantiations. For the sake of the video people, I'm going to try and do it this way. Okay, and I'm going to come right here. And let's go ahead and make the instance. Well, I could make the instance inside of a test bench. In fact, that's how I'm going to do it. I'm going to make it inside of the test bench to kind of show like the test bench setup or something like this. So we're going to have something, we'll just call it, I don't know, C0, that is an end shift. And it's going to have I'm gonna come out of here, fine, generic map. So I declared the component the exact same way on where I would write entity shift register, it has a generic blah, 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 it has a port, blah, 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 right? I would do the same thing, just copy and paste. I'm not writing the declaration because it's the same copy and paste method, you're good to go. The instantiation has this one change that it says, hey, CO and shift generic map. And let's say I want to make it an 8-bit. Well, if I want to do that, I would just say 8. Now I'm making an 8-bit shift register. It then will have a port map. I'm going to run out of the video screen, but you could just write this all on one line or have a return. It doesn't actually care. Of a port map and just saying, well, it's going to have these signals input, and we'd probably call this like, I'll do this as a test bench, right? So in TB clock TB reset TB and I'll call the output S. Sure, I'm staying on screen. Yeah. Okay, so that is it. I've made an 8-bit shift register. If I wanted to change that to a 4-bit, it's not 4 bits. That's how easy this is. Now, it would error out if you put a 1, because it would go, well, 1 to 1 would cause an error. So it's got to be at least a 2-bit shift register. But I mean, a 1-bit shift register is just a register, and you've already got a component for that. So anyways, that's our generic map. Now, if we were to test this, right? Did I do the timing diagram for shift registers? I think I did, right? Where if I put a 1 in for just 1 clock cycle, so this is in, this is clock. Then I have, well, a 4-bit, so what would happen, right, is this rising edge of the clock, they all start at 0. On this rising edge of the clock, this one is going to clock in that 1. And then at the next rising edge of the clock, it's going to clock into 0. And so on, right? We're gonna see that 1 shift all the way through. Here, okay. I'm going to see if this overhead projector is going to play nice. Overhead controller is It did, great. Okay, so, oops, one project's open. Huh. Good, I got freakishly big text, we're good to go. Okay, so here's that n bit shift. I just want to show you guys like the real code so that you can see like everything as it is rather than kind of just my handwritten kind of some for comparison. Okay, so here's the generic declaration, right? That's saying that this has a generic type port. And then the ports are declared the same way, but uses that n to make that output vector. Okay, now I've declared the component reg, which I'm not going to go into that code. I think it's simple enough, right? That has D, clock, and reset, and a Q output. I've declared that signal int s of a standard logic vector, once again using n, and then I just say begin. So this shift register, the reason that the first register can't be in the generate statement is for all other registers, int s is used as the input. Whereas in the first one, input is used as the first input. Now, there is probably actually a way to write something like, how would I probably do it? Like int s at 0 gets assigned to input, and then make my int s like 1 bigger or something. And I could probably use that to make my generate statement for all of them, including the first one. I haven't thought too much about it. This was just the first way that it popped into my head, so that's how I went with it. And the reason is this one signal. That's the one that's problematic for everything else. Okay, then I have the loop name, generate shift, loop range, and instead of saying begin like you do in a regular for loop, it says for blah 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 generate instead of for blah 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 begin, right? That's the difference. That's its names as the reg port and generate, and then I assigned the output Q to that internal signal. So if we go and look at sources, this is a little bit smaller. I'm sorry, I don't know a way of making that particularly bigger. But it has generate shift at loop 1. Yeah, and it's doing the weird shift X1. But you can see that I've made a 16-bit shift register here. And it has each of those instances and shows me where the loop variable was when it did it. Yeah, the naming schemes on this are not my favorite, but they work. And then if I open up my test bench, I just declare that component. Sorry, I was testing two different things, ignore the upcount one. Okay, component and bit shift, right? I've just copied and pasted and added, and it has this generic. I didn't have to add anything. I just copied that over from here, right? I just copied and pasted this, threw it in the component, changed the word entity to component, and then said end component. Created my signals for the test bench. And then here's the declaration. That shift 8 has a generic map of 8 and has this port map. Once we start using clock thing, this is my favorite way of generating clocks, that line 51. So as long as clock starts at a value, you have to make sure it starts at a value. So that's what this is doing here, is saying clock, reset, enable, and input all start at 0. Now I can just say clock is equal to not clock after 5 nanoseconds. What that means is every 5 nanoseconds, it'll change from 1 to 0, 0 to 1. So I have a clock period of 10 nanoseconds, right? I get a rising edge every 10 nanoseconds. So that means my clock frequency is 1 divided by 10 nanoseconds, right? Remember that relationship, the clock period to clock frequency? Okay, that's an important one. It'll show up on an exam almost certainly. And then I just write my process. I didn't do anything fancy. I waited for a little bit. Remember I said reset started at 0. So I reset it, go back to 0 to make sure I'm at a known location. That's all these first 4 lines are doing, is creating a reset condition so that I know where my circuit is starting from. That's just good practice. And then I wait for half a clock period, roughly 6 nanoseconds, right? Assert the input to be 1, turn on the enable, wait for a clock period, turn off the input, and then just wait. And what this should do is I should be able to watch that bit, that 1 bit that I had for 1 clock period shift through all of those values. Let's find out. So the S output starts as undefined, that's that orange U. But other than that, you can see that actually, I'm going to make this bigger so we can see it all. So here's input, this line. I know this text is a little smaller too, but I think it's okay. Has that 1 clock period of input. So that rising edge of the clock, where this yellow line is, triggers the first shift register, bit 0. And you'll notice that there are 8 bits, because I said it was an 8-bit shift register, to clock in that first one. And then bit 0 gets clocked in as another 0, because it's 0 is the input. But we get to see that march through that shift register. Anyway, that's shift registers, generics, and generate statements. Any questions on those?
Okay, so the clock statement you wrote, that will repeat throughout.
Yeah, it will just keep going. So that 1 line generated this clock the entire time
That's all.
that will run forever. Yeah, so that's my favorite way to create a clock. You'll see other examples of it. I recommend just using this one because it's not prone to bugs. The biggest error I see students make with that one is not starting clock at a value, right? Because what is not clock of unknown, right? Other than that, it's hard to mess up. Great, other questions? Feel free to pull up this video. I'll throw it on my YouTube channel, and it'll also be in Kaltura under the modules tab, I believe. And so if you go to Canvas modules, there's a link to Kaltura videos that have like closed captions and stuff. Or you can just go find my YouTube channel, which I have a bunch of, all of the lectures are public videos. Then you can go steal all of this code. If there's an issue with the Zoom on this that you can't see or whatever, I think I have it set up right. I've had issues before, and that includes for anyone watching this online. You can email me and I'll happily just post this code. If there's issues. Otherwise, I prefer you to write it yourselves just to kind of go through the motions of it. Okay, good. I hope everyone is comfortable with that. Oh yeah, I think it ended my meeting. Oh wait, no, I'm recording on this one. That's why. Okay, let's go double check that. Okay, yes. Hopefully, it looks like I had that point in the right spot. Hopefully nothing went weird. That'll get posted. If it was weird, just ask the code. It's easy to simulate yourself and learn from it.